So, as I was saying, uh, thank you for joining us today. We are doing a series on all-weather investing, Sphere PMS, and today we're going to be talking about semiconductors. So, in 2023, AI, big tech has been a very hot theme, and the substance that actually fuels this entire theme are semiconductors. So we wanted to curate a conversation around how this industry works, what its history has been like, what valuations are like, and all of these things. So we look forward to your participation in this conversation. If you have any questions, feel free to type it into the chat box. We will keep some time towards the end to do Q&A. So with that, let me just begin our conversation for the day, and I'll walk you through what the industry has been like. So from the 1980s till today, we've had about four eras of computing, right? So the first era is basically the 1980s to the 1990s, and I'm sure a lot of us actually remember some things from this era where you had mainframes, right? So mainframes were also referred to as iron boxes because they were huge, massive machines that were capable of executing large computations and storing a lot of data. So, but the trade-off was that you would have these devices that you couldn't really port anywhere, right? So you had to work completely on site. And to resolve this issue of not being able to take your data elsewhere, even though you were able to store it in one place, you had the personal computer come in, right? So the personal computer, I think all of us would remember, like in the 2000s, how it would be probably one person in your neighborhood would have a computer in their house. And as kids, we would go to that house to play. And it was always like a very regulated thing, right? In the 2000s, that's how the personal computer phase was in India. But then you had the laptop, and then we went to as tech improved, we were more along the lines of one device per person. All right. So then we got to the PC plus internet era. And so basically, what is the history of the internet, right? So it's something so common, but a lot of us don't have an understanding of how we got to this era. So initially, when you had a computer, that is your mainframe stored data, but it couldn't communicate with other devices. And then there was a way to the whole concept of networking allowed devices to communicate with each other as long as the device was in the network, right? So you would have isolated networks, but the networks couldn't communicate with each other because they were talking in different languages, so to speak. So the invention of the internet actually needs to be credited to the US Defense Department because they were interested in having a system that would allow networks to communicate to each other, because you'd have, say, intelligence data in the US, which was one network, and then you would have actual soldiers on field who were operating on a different network, but there was no way to communicate information from this network to the other network. So this inter-networking, that's where the internet actually gets its name from, because you're now allowing not just devices to talk to each other, but networks themselves to communicate with each other. So that revolutionized the way that computers could be used. And initially, while it was meant only for the defense, it eventually became more of a commercial and civilian tool, right? So then you had email, then you had different sort of social media platforms, and you can see how that changed a lot of things. So, but now with the internet, you were able to communicate with anybody across the world. But what about uh, actually having devices? What about actually having devices that would allow you to take your data from one place to another? So instead of porting the device, you wanted to make sure that you could port data itself, right? And that's where the solution of cloud came in. So now the very fact that we're able to work from home, the fact that we're able to transport data from one place to another without actually moving your device, while it seems something that we take for granted today, there was a significant portion of time where you weren't able to do that, right? So with each of these technological innovations, you've also had a lot of revolutionary change that has happened, right, in the way that we use data, the way that we're able to store data. So the cloud also expanded the amount of data that we could store, and then you had big data come in, and big data essentially collected lots of individual pieces of data that you could analyze and then see whether it forms a trend. And because you have big data, you've had things like machine learning, and because you had machine learning, then you're able to teach machines to actually learn, and you have what we call artificial intelligence. So each of these eras has basically doubled the size of the semiconductor market. So if we move from, let's say, the size of the semiconductor market in the mainframe era was 1x, then by the time we got the PC era, we were at 2x. By the time we got to mobility to cloud, we were at 4x, and now we're going to go to 8 times that number, right? And the path that most people are looking at projecting is that this industry alone could become $1 trillion economy, right? And that is one of the reasons we wanted to discuss this topic with you today. So I'm going to do a quick poll, which is essentially to look at who was the father of the semiconductor chip. Was it William Shockley? Was it Gordon Moore? Was it Robert Noyce? Or was it Nikola Tesla? You can just type in your answer in the chat box. I see one response here. I can. All right. So one for William Shockley, a lot for Gordon Moore, a couple of. Okay, great. So the correct answer is actually William Shockley. And we need to talk about why he was the father of the semiconductor chip, right? So before the semiconductor chip, the reason we need semiconductors is that you need electricity to pass through a particular circuit. And before the semiconductor chip, or before you had something known as a transistor, you basically used to have this cathode ray tube. So you needed a vacuum, you needed a tube, you'd have one end that you charge positively and the other end that you charge negatively, and then you'd have the flow of electrons in that direction to equalize the charges. But what Shockley did was he realized that you could actually create a transistor. So today the most common form of transistor is the NPN, right? So you have a negatively charged plate, you have a positively charged plate, and then you have a negatively charged plate. And then you have this flow of current that happens here by connecting all the ends to different terminals. So how you create this is actually one of the key ingredients in a semiconductor chip is silicon, because they realized some of the properties of silicon makes it like a good semiconductor. And so you would add certain impurities to improve the conducting power of this transistor. And so the transistor kind of revolutionized things because it was so small, and you could connect many transistors together to form chips. So you can actually see, so in terms of just understanding how tiny this is, right? You're talking in nanometers. And for scale, you all played with little marbles, right? So if we're thinking about how much a nanometer is, compare the size of a marble that you've played with the size of the planet that we live on. That is the scale. So this is not even a grain of sand. It's not even the end of your hair. It's much, much smaller than that. And on that, you can create many transistors that form an integrated circuit, and that circuit is used. So your phones typically have like 1 to 2 billion transistors. Like today, I think the average modern mobile phone would have about 2 billion transistors on them, right? And this is why, uh, so if you're looking at something that is so small, right, so tiny, that you can understand the level of precision that is involved in maintaining or even designing these things, right? The level of skill that is required to get an output so that your phone works properly. And I think just to give you a sense, this week we've had the launch of Apple's M3, M3 Pro, and M3 Max chips. But essentially, like these are all the things that are powering our everyday devices, right? So if we look at the Internet of Things, things that we take for granted today, you wanted to have a smartphone, you want to have wearable tech, a smart watch that will tell you if your heart rate is up or down, or how many steps you walked in a day, or if you're looking at even inanimate objects like your house, you want to have you want to walk in and have your AC on. As you move, your lights will turn on and off. You don't want to get up to switch them off. These are all powered by semiconductors. We don't realize how much they are part of our everyday lives. Or even if you look at, you don't need to have a smart car. Anything like if your dashboard itself is electronic, right? If you have a display, there's a semiconductor there. You don't need to have a self-driving car to think that, oh, there are semiconductors in my car. There are semiconductors everywhere, and they're so well designed. Uh, and it's only because a lot of effort actually goes into this process. So, how are chips really made? I think one thing in terms of understanding how they're used is that the larger the chips are, they are going to be in more mature industries, right? So where you don't need such fine computing, such fine display. So typically your larger size chips are used for sensors and are better with smart control. Then as the computing intensity or what the brain that's required for semiconductors to work, then it gets smaller and smaller in size. So things that are used in a supercomputer would obviously be much smaller size. So today we are talking about Apple's new chip, right? That's 3 nanometers. It's on the more advanced side of the scale. Okay, so now getting into this whole value chain. So the value chain basically tells us what is happening. How does a semiconductor go from being where it is to where to what comes into your hand? So the first is you actually need people, and these are highly skilled engineers and designers who can work with these materials, who understand how these materials work with each other. Then you get into the design part of it. So designing a chip actually is expensive. You can't, this is not like a prototype that you can make one chip and then be like, oh, does it work? Does it not work? Right? So even the design process is actually done on a virtual scale initially. So you have specific softwares um, that like Cadence and Synopsys that can help you design a chip. So you can decide what the output you want is, and then you can tinker around with the design. Then you can sort of virtually test it. You can see whether it works, whether it doesn't work, what you want to modify, and then you can run simulations. And based on those outputs, you have a design prototype. And once the design prototype is set, then you begin manufacturing it. So Harshil will actually take you through a detailed process of how the manufacturing piece really works. And once you manufacture a chip, you actually have to assemble it, right? So chips don't work in isolation. We've talked about how your phones could have up to 2 billion chips in them, right? And that means they need to come fit together in some way. That's a puzzle that you have to put together. And once you get into package and assembly, you actually have to test. So does this work? Does it heat too much? Is it going to blow up? How long is it going to last? These are all parts of your testing phase. And then you assemble it onto a board which goes into a device. And of course, you have the logistics piece which would basically get your product to the end user. And finally, you have your customer, which is who are people like us. So if we look at this industry, right, when we think about the names that are there in this industry, we can only think of the top 5 or 10 names. But there are so many companies that are involved in this business. There are more than 100 core companies, and we need to think about how these are spaced out. So if you have fabless chip designers, so fabless essentially means that these people only design the chips, they don't fabricate or manufacture them. So, I mean, our favorite pick, or rather, everybody's top hot pick for 2023 has been NVIDIA, right? So, NVIDIA designs chips. So, different companies that use semiconductor chips could hire NVIDIA and tell them that, okay, we need you to design this chip for us, and this is where we're going to use it. And that's basically what these companies do. And then you have integrated device manufacturers, and these are essentially companies that will both design and manufacture chips. So on one hand, they're looking at what kind of chips they need to use, and on the other hand, they're actually going to produce those chips. So companies like Bosch or Intel or Micron, these are involved in the integrated device manufacturing space. And then you have foundries. Foundries are basically your manufacturing hubs, right? So let's say Apple has a contract with TSMC and they tell them that, okay, we need you to create this chip for our phone. Then the design is already done and it's sent over to a manufacturer. And you need to understand that the skill sets that are involved in each of these domains are actually very, very different. The kind of things that each company does is like very niche, right? So semiconductor is a broad term that we use to club all of these companies together. And then even to do what foundries or designers or any of these people do, you need equipment, right? So one of the biggest players, ASML, has a monopoly over the market in certain segments. And then you have your design, your IP. So we talked about Cadence and Synopsys. These are different softwares that are used to design chips. And then you have your testing and packaging. We talked about that portion of the value chain. And of course, it goes without saying that you need the raw materials, right? So outside of silicon, so silicon is the base conductor, but you also have to dope it, that is, add certain impurities so that it becomes a conducting material. But the level of purity is so high that you would need different agents to clean it. You would need different ways to create like a wafer. So wafer is basically a thin strip of your semiconductors. And I think your last thing is we'll start the process of how the value chain is created. So I'll begin with design and then Harshal will take over from that. So I think this week, like when you see all of this in the news in terms of how, like, what is happening, what does it actually mean? So the M1 was their first generation chip that Apple designed, and then you had the M2, and now you have the M3. So that's what the 1, 2, and 3 actually mean, right? When you see up to 8 core GPU, 16 billion transistors, so the more number of transistors you have, the more specialized that chip is actually going to be. And the higher your core GPU is, the higher the resolution. So GPU is your graphics processing unit. So that just tells us that it's going to be a much more powerful tool in terms of visualization. So the M1 was 8, your M3 Pro is 18. It also, the more number of transistors you have. So we've gone from 16 billion to 37 billion. So in 2 generations, you're basically doubling the number of transistors on a single chip. And you can see that essentially what this actually means is that your computers are going to be faster, they're going to be more energy efficient. The graphics and the visuals that you get out of your screen are going to be much, much clearer, right? And the smaller your nanometer size is, so the M1 was around 5 nanometers, the M3 is around 3 nanometers. And this is the first time you're actually having a 3 nanometer chip used in a personal computer. It's never been done before. And yeah, I think with that, I will hand over to Harshil.
Thank you, Samyuktha. So I think, uh, see, we've been tracking semiconductors for the last 2 years, and a lot of things have happened in the last 2 years just regarding this sector, in terms of market leadership, in terms of geopolitics, in terms of new technologies that are being developed, and the use cases for it also. Right. Now we went through the design part, and so when I was also trying to understand the entire process, I tried to speak to myself about, how is it really being manufactured in the language in which I would understand. So I've tried to keep the language extremely understandable. I've kept it extremely simple. I'm not going to be telling you anything more technical. There might be a few technical terms, but I'm just giving you a disclaimer. Not much of technicalities is what I would cover. Right. So the first step, right? You look at a wafer. This is not something that you get outside, but what is a semiconductor in general, right? It's what is a chip, right? So basically, it is just sand, right? It starts with sand, but it is silicon-rich sand. So it's sand. There are grains. What do you do with the grains? You can't really make it into a small chip. So they heat it, and once they heat it, it becomes into liquid. After that, that liquid is then solidified into an ingot. So it's huge. It is huge. And what they do after that is that they slice it. They slice it really, really thin, and it's large, right? So the larger the diameter of the wafer, that's what they call it to be the wafer. The larger the diameter, the more chips you can get out of it. So when you see, when you read articles or when you see it on social media, that shiny thing, that round shiny thing, that is your wafer. That's your wafer chip, right? And that is polished. So once they slice it out, it's still grainy, it's still a little rough. So they polish it. Right? So they polish it, and then that's how they get that shine. So that is your wafer manufacturing process. That's the first step. Then what do they do? So we know when we go out in the sun, we are told to apply some sort of sunscreen. It's a protective layer. We have to protect ourselves against UV rays that are coming out. Likewise, the wafer is then protected with a thin film, and that film, and this process goes on multiple times. There are many thin films that are being applied here, right? So there's a thin film that is applied on the wafer to protect it in the process is going forward, because the process, it's a very tedious process for the wafer. So that process is called oxidation, and they do that with the help of vapor and oxygen. Right? It's just a thin coating. It's very, very thin. Now the next important step. This is called photo lithography. Now, this is where your design comes onto the wafer. Are you able to see the screen? I don't think it's moving forward. I think it's stuck for me. Yeah. Yeah, you can move on to the next slide. Yeah, this one. So this is where your design actually comes into play with the wafer. And how does this really take place? Now, what happens is it's like how you develop photographs in an old camera. We used to go, we take the roll, and then we would go, and then we would develop, and only then we would get the entire photo. So this is how they do it. What they do it is they would put the photo mask on the wafer, and they would throw in light, very, very bright light, and that's how the design gets made onto the wafer, right? And they're very, very, very small. They're very, very small. So you need extreme precision and extreme technology for that entire design to come onto the wafer. The mask, the entire mask to come on to the wafer. Right? You can move on to the next slide. Yeah. So who is the largest lithography equipment manufacturer in the world? This is a good poll. Is it Apple? Is it Taiwan Semiconductor? Is it ASML or is it Nvidia? You can put in your answers in the chat box. I think we're getting answers on B. There's ASML. There's ASML again. There's Taiwan Semiconductor. There's ASML again. So most of you are right. Yes, it is ASML. ASML is the largest and the oldest lithography equipment manufacturer in the world. They went from DUV to EUV, and EUV is more sophisticated. It's more stronger than the previous process. And this is where they come into use, where they help in the photomask, or they help in that process of blasting light onto the onto the wafer, so that the design of the chip comes onto the wafer. Right? I'll give you an understanding of what it really looks like. If you can just move on to that. This is what it looks like. It's one of the most complex machines in the entire world. They don't make more of it. And anybody who uses ASML, or anybody who uses these machines, like we saw in the previous slide, where there were many players, there's ASML, there's Applied, there's Lamp, whoever uses these technologies, they have to go back to the same player. They cannot change the player. They have to go back to the same player, because the parts and the servicing that comes along with it, only that player can do it. This is exactly what the machine looks like. And I've taken this from ASML itself. Okay, so it's still not conducive for electricity, right? So what happens is there is a process called etching and deposition. Again, so once you draw the entire design onto the onto the wafer, what happens is there are many parts within the chip that you don't need, right? Once you design it. So etching is that process where they take off all the design parts that you don't really require, right? But it's still not conducive for electricity. So what do they do is, this is a process called ion implementation, right? Ion implementation is basically they include impurities into the entire design to make it conducive for electricity, right? And these are basically your aluminum, titanium, tungsten. So it's just a coating in which it makes it conducive for electricity. Basically, electricity can then pass through it, right? This is what would make it more powerful. This is what would make it. See, when you have heating issues, then it's this problem. Right? There's something wrong with it. There's something wrong with that entire design process, but this process was not really done well. Right? Then there's the next step. Now, this is basically sorting out defective chips. Once you figured out, once everything is drawn, once everything is taken off, once they start getting conducive for electricity, there's something called the yield. Now, this is basically the number of working chips divided by the maximum number of design chips. Now, let's say you have a very large diameter, and within that, there is only 30% that is usable. Everything else is defective, which means it's a horrible number. You can't really use that. Right? That means that whole process is gone for a toss. This is why you need a very, very strong foundry. This is where you need players like Taiwan Semiconductor to come in. This is where you need players like Samsung to come in, because they have a very good history of a very high yield. Right? And that's why you see TSMC is getting a lot of contracts from Apple. TSMC is getting a lot of contracts from other players as well. That no, we'll design everything. You come and please make my chip. Your yields are really good. I would rather have you than to go to somebody else. Right? But the problem is that with every technological advancement that comes in, right, even TSMC, that is basically has to get. So once the design guys up their game, the foundry guys need to up their game. The foundry guys need to up their game. Then the manufacturing guys need to up their game. The testing guys need to up their game. The packaging guys need to up their game. So everybody in the value chain needs to up their game. So it's very difficult for each business to be replicated. Right? And that's why there's a market leader for every single manufacturer in that entire value chain. Right? So this is where the sorting out of defective chips comes in. Once this happens, then they move on to the next step. Now, this is packaging, assembly, and testing. Now, this is the last part, but this is also one of the most important parts. You have everything in your hand, but it's still not gone onto the circuit board. It's still not packed. It's still not bonded. Now, this is where players like Applied Materials come in, where after the wafer is cut out, you have small semiconductor chips that come out of it. It's bonded to the PCB board. After that, it's wired to the PCB board. That sort of bonding happens, and then it's molded. Right. After it gets molded, then there's a good stamp that comes on for the company, and then a final test it goes through a testing process in which they see everything is working according to their plan. Electricity is going through, it's working well with the PC or the laptop or the mobile, and only then it is rolled out. Now, another poll: how big is a semiconductor foundry? Now, these are very, very interesting options. 968 football fields. Would it fit 628 Airbus A380? This is a very big plane. 4 lakh Tesla Model X. 1.59 billion iPhones. So put in your options in the chat box. Okay, the first option, somebody has put A. That is 968 football fields. Okay, not bad. Okay, then we have a B, 628 Airbuses. Okay, we're heading somewhere. Okay, we have one more A to B. Okay, we're going neck to neck. Okay, we have a very interesting option, maybe all. You are right, it's all. You are absolutely right, it's all. So imagine 968 football fields. That's the size of a semiconductor foundry. This is what the foundry really looks like. This is the plant that's coming up in Arizona. It's a $12 billion plant by TSMC. And this is what it looks like. 968 football fields, 4 lakh, almost 4 lakh odd Tesla Model X's, 1 billion odd iPhones. And to give you a perspective, since iPhones start, Apple has done about $2.3 billion in iPhone sales. That's from its inception up until now. And half of that would cover up the entire $12 billion foundry. And so let's look at the economics of a semiconductor plant. How can I really come up with a plant? So you need people, you need land, it requires a very, very high investment outlay. Not many people can spend. And I have a very interesting chart of all the players that are spending money to come up with new plants, right, to come up with new foundries. Right. And I also have some number on recurring R&D costs. You would see how difficult and how expensive it is now to design chips. Right. The most important is clean water supply. See, because there is that process of oxidation where you require water and vapor, right? And then in the etching process, right, you need then there's wet etching and there's dry etching. Again, you need chemicals and you need vapor, right? So clean water supply is what they require, and consistent power supply. See, the world is heading into a place where there is high demand for these chips. There's a high demand for these products. It's going to be everywhere, right? Whether it is AI, whether it is in a mobile, everywhere these chips are going to be. And power is your new data. It is everywhere. Even in India, if you see, we are having all-time high power demand. Yet we have not yet gone on to renewables. Right. So the economics is simple. The number of people involved need to be extremely skilled. You need to have land as big as 1,100 acres. This is what the plant is. The size of that plant that I showed you, high investment outlay, $12 billion is nothing. There are players committing $100 billion for high advanced technology. Then there is recurring costs, clean water supply, and consistent power supply. If you can move to the next slide. Right. R&D will not stop. It is not going to stop. If somebody comes up with a chip now, 3 nanometer is just starting to roll out. Before that, we were on 5. The first chip that Apple came up with on their own was M1, which was 5 nanometer. And immediately after that, 2 years in 2021, 2023, so things are very fast. Advanced is extremely fast, right? We are already seeing TSMC committing huge sums of money in Taiwan to come up with a 1 nanometer plant. You can't even see it with your eye. That's how small these chips will become. And imagine the testing that would happen and the players that would be involved in testing and packaging that would have to go through advanced technologies. There would stacking. There would be newer technologies that come in that we won't even be able to anticipate. Right. So always R&D will happen. R&D will not stop, and this is why the industry is enabled for newer technologies to come in. Right. As and when it scales up, it will become more affordable to us. So now you see how expensive it is to design even a 5 nanometer chip. This was in 2020, and design costs are rising very, very fast with each new node that comes in. 65 nanometer that was in 2006, which are old, right, which are mature, and these are chips that are that get used in auto. Right? They don't get used in advanced technologies. They get used in the auto sector. They get used everywhere else there. Right. So over 18 times is what the cost of designing a chip has gone up with each new node that comes in. So it's going to keep on getting more expensive as and when we reach that particular scale. 5 nanometer rolled out in 21. Everybody started using 5 nanometer, and now suddenly we are going up to 3 nanometer, and then we would go to 2. Right. But as and when more products keep on coming in, as and when technology keeps developing, things will start getting affordable, but the cost would still remain high. So who's really committing that money? Let's look at the investment outlay. Right. Here we have 3 players: Intel, Taiwan Semiconductor, and Samsung. So if you see, Samsung is dominating on the Asia side, Intel is dominating on the Europe side, and Taiwan is sort of dominating now on in its home ground, Taiwan, and the new plant that I showed you in Arizona. Somebody has commented saying, I live close by to this factory. It's been under construction for a very long time now. I would love to have this conversation with you offline. Okay. But if you look at the investment outlay, everybody has sort of committed more than $100 billion, right? Collectively put together, it's more than $100 billion for each player. Right? That's how expensive it is to come up with a semiconductor foundry. That's how expensive it is to manufacture chips. Right? And it doesn't stop there. The thing is, we are having a good amount of government support that comes in. Right? Most of the research and development that you see is not just the private players. No, majority of it is funded by the government, and US is playing a major role to regain and to make themselves competitive. Right? To maintain that sort of leadership, they're still committing to more money. They've come up with the CHIPS Act, and though it is in the starting stage, but it is very, very expensive to come up with a plant. It takes about 20 to 25 billion just to come up with one small plant. Right. So let's look at how India is going to play a role in this entire value chain. How are they going to come about being or playing a role in semiconductors? Right. So this is the ecosystem. India houses 20% of global semiconductor design engineers in the world. If you look at our entire ecosystem, we are everywhere. We are part of each organization that plays a role in designing chips, in manufacturing chips, in testing, in technology, in EDA, everywhere. So we are everywhere. Right? We have always been everywhere. We have exported talent. And now we are trying to bring that talent back in. Now we're trying to house talent in India, where we can support skilled engineers and develop semiconductors in India. So what is the financial outlay that and the fiscal outlay that India has sort of committed to? So India has committed $30 billion. It's very, very small, but it is very, very much necessary right now. It's actually a very high amount if you look at how we've not started, and we are willing to commit so much money in terms of fabs, in terms of displays, in terms of design linked incentive, in terms of production linked incentives, where we are willing to commit the sort of seriousness that we want to show to the world that yes, we are and we want to become the manufacturer for the world. Right? Back then it was make in India. Now it is make for the world, and this has it's a very big transition that we've seen not only in this industry. We've seen this in multiple industries, be it textiles, be it auto, and now we're trying to do it on semiconductors. Right. So we have committed to a very big investment outlay. We are getting players from outside that are supporting our journey, that want to commit to India, and they look at India as a very, very big market. Now we've taken too much time. There is some time for Q&A, so I think I'll open the floor for Q&A. You can put in any question that you have in the chat box, and I'll do my best. If it's about the process, I will be able to explain it much better. Outside of TSMC and ASML, which are the segment leaders that are listed in the stock market? I said there's testing, and within testing, there's KLA, there is ASML, there's Applied. Then in each of the process that I said, ion implantation, be it etching, be it deposition, each of them have specific players that are listed in the stock market. If you just go anywhere and type in semiconductors, you will get the entire list. There's nothing that is really difficult.
Yeah, I can just take us back to that slide with the players in the industry. I think there are many, right? So we saw Qualcomm, we saw Nvidia. You have different companies in the listed space. So there are. Let me just go back to that slide.
There's Tokyo Electron, which is a very big player. See, you have to understand that this industry is not new. This industry has been there for a very long time. And before the leader was Japan in terms of memory. So I'm planning to do a memory webinar also later, where we try to understand the entire memory space. When you hear 256 GB, you say, yeah. So I want to address how 256 GB has actually come up to be 256 GB. And now what really goes into it becoming the entire value chain of how it has developed, the players that have developed out of this entire semiconductor and memory process. So in India, who is the leader in semiconductor industry? Nobody yet. Nobody yet. People are willing to commit money, but nobody yet. Is there any independent PMS for semiconductors? But I thought no. Right now, there's no product also in India where we can invest in semi ETF or semi fund of fund. Tata had filed it, but it was during the time in 21 where US markets had crashed, and it was very difficult for them to get approval. Right? After that is when RBI came and said, no, you can't go beyond a particular amount in the US. You can't invest so much. How the semiconductor will help the growth of the Indian economy? See, you have to see this as it's not just about the economy. It's about how we are going into we went from make in India to make for the world, right? And if we are able to play a very important role with every country, that would in turn benefit our economy. Indirectly, it would benefit. If we are giving them something, they would naturally give us something. Is it a good time to invest in the semiconductors industry? It's a very good time for you to watch it like a hawk. See, the thing that is happening in this industry now is that in 21 you saw, in 20 we were sitting at home in 2020 and the demand for these chips skyrocketed. So it takes time for new capacity to come in. And after that, if demand goes down, we came back, we started going to, it was after work from home, we everybody started to come out, everybody got back to normalcy. Now, in that normalcy stage, you had a excess inventory, and now the industry is going through this phase of excess inventory. And usually, in any industry, in any sector, when we do see that inventory levels are very high, naturally, you should be cautious. Is it a good time to invest? Yes. You should look at it like a hawk. We need uninterrupted current supply and clean water for semiconductor manufacturing. Do you think it is possible for India to manufacture semiconductor? 100% yes. 100% yes. If you look at the plan, it's in Dolera, and I did not want to put that here because it'll become too complicated. But I put the source. You can just type in Google semiconductor mission in India, and you would get the website. And then if you go to the reports, you would get presentations that they have done. So they have a clear roadmap of how they want to go about being a leader in semiconductors. It's not leader, but yes, they would play a big role in manufacturing chips. So you see, so it is happening in Dolera. They have already named the city Semicon or Semi City, and definitely clean water and uninterrupted supply of electricity is happening. You have not had any interrupted supply of electricity even now, right? We've had this is an El Nino year. We've had scattered rainfall, right? So usually in these phases, you do have some sort of power cuts, but we've not had power cuts, right? Be it for industries or be it for us, right? So and it's peak demand, so we are able to service it, and most of it is fossil fuel. And players in fossil fuel are also committing that yes, we would be able to do more. We would be able to supply you more coal. We would be able to supply you more of this. Keep the industries going. Keep everything going. Don't worry. How difficult it is for a new player to enter the chip business, like Tata's and many others. See, it's not. See, they would not be doing this alone. You have to understand that these are chips that used to majorly the research and development was done for defense, right? And there would be government support that comes in. It's not just so when you hear Tata's tying up with NVIDIA or Reliance tying up with NVIDIA, definitely there is a good exchange of technology that happens, right? So this a small player cannot do. Right? You need a big player to sort of join hands with a big player, and that's why we have been talking, and we have even in our letters that we give out to our investors that yes, this is a time where and we give out multiple content, right? That this is a time where we should look at the bigger players, we should look at the leaders, right? So yes, big will join hands with big, and that's the benefit. However, there will be smaller players that also benefit out of this because of demand that comes from the big player, and they will be able to supply it. But it is very difficult for a new player, not for the big player. So in India, there is nobody listed, but Synopsys and Cadence is listed in the US. Wolfspeed is also listed in the US. Whether some companies look overvalued to you, yes, there are companies that are overvalued in the semiconductor industry, and that's why I said that yes, you should definitely look at this. When there's a mismatch in valuations, there you should be cautious. You should look at it like a hawk, but be cautious. Which phase has the highest margin or the deepest moat? The packaging and the testing guys, definitely you have to go back to them, right? The foundry guys, they are the only guys who can make you the chip. Nobody else can make you the chip. And within that, there has been a wave of consolidation that has happened over years. And there were many players in the memory space, in the foundry space. That gives you a good idea. And over a period of time, the consolidation has happened. So now there are not many players who can make you the chip for you. So there's There is Intel, there is Samsung, there is Taiwan Semiconductor. So it's not about having a moat. It's about how I cannot do this. Nobody can replicate this. So naturally, I have to go to them. Second would be your equipment players. Again, if I'm choosing a particular uh, uh, supplier of equipment, I have to go back to the only, because if I change it, then the guy who's giving me the demand will go away.
Yeah,
My yields
also,
will drop.
I think adding to what you said about equipment, right? There was a really good podcast that we listened to on ASML, and they are literally the only manufacturers for certain types of equipment. So, in that sense, you could have somebody who's doing something very niche and there is no competition and there are high barriers to entry. But that can be on any part of the value chain. It doesn't necessarily have to be only in one thing. And it's not that certain segments of the value chain tend to have higher margins. It just depends on how that but how much of an impact that particular company has and how much of a market share they have in the value addition that they're doing along the chain.
See, every part of the process is extremely important, so they have to go there, right? But it's just about who's having the pricing power. Right? So in the foundry and in the equipment player, with the equipment players, the pricing lies with them. But they have to go hand in hand. They cannot charge you exhibited rates. Right? So they will charge you in the other aspect, that is more of the services side. So every part is very important. In the Indian market, can Tata Elxsi be classified into the design segment in the value chain? So I don't know, but I do not want to comment right now on. I don't even know what will develop and what are the developments that can happen. So I don't want to comment much on that question. Do you have any front runner in India to capitalize the semiconductor manufacturing in India? See, not yet. There are players who have tried to come in. There are players from outside who have come in here. So there's no front runner yet. So it's like EV. So before you had Tata, and now most players are coming out with their EV. Then there is a leader now coming up to be in hybrids. So it's very difficult to know who's going to be the leader, but something would come out in the future for sure. Doesn't certain phase of manufacturing require huge quantities of water? Yes. What happens to the water? So so what they're doing in the Arizona plant is that they are reusing that water. And it's not like we are not in 2010 or 2005 where we go and dump it in the ocean or something like that. There are new technologies that are coming up. There are new processes that are coming up where we can reuse this water. So that plant is sort of going to get reused for water. The other plant also that they are doing gets reused. There are videos about this, which I think you should. You can just see it on YouTube. Is
Can
NVIDIA
take
having a
this
monopoly?
last question?
Yeah. Is NVIDIA having a monopoly in the GPU space? Are other competitors catching up for this demand? First, I think you should ask the right question. For demand is there, but supply has to come in. Right. So it's not about demand. Uh, uh, I can go to NVIDIA saying, hey, I want this particular technology of yours. I want this particular chip. So I'm giving you this much order. But then unless and until it comes into the system, it's not real demand. And the next one more trend that is happening is that you're seeing monopoly players like Apple, Google, and Microsoft coming up with their own chip. So Apple has come up with their own chip. Google is trying to come up with their own chip. Microsoft is coming up with their own chip because it works for them. There are specifications that only they can sort of use, and that's working out well for them. So we don't even know whether they will go to we don't even know whether they will go to somebody like NVIDIA later. But yes, right now their technology is unbeatable. Arizona has well-tested water treatment and distribution setup, something that India does not have yet. I would suggest you to look at what they are doing right now in the semiconductor city. What made the market dislike Intel, which used to be a leader, to be little blunt in when you lead, you have to, and this is an industry where you have to continuously spend money, have the right direction, and only then you would be able to sustain that sort of monopoly, right? And that is what they were not able to do. There were multiple internal issues that sort of got housed over years, and now definitely they are lagging. But they also have plans of 2025 to come up with more advanced foundries, more advanced chips. So I think we can close. That was the last question.
Thank you everyone for joining us. This has been great. We hope we can have more conversations with you on this theme of all weather investing. And we look forward to seeing you next time.